Okay, so it's a pleasure to have Ritam Sinha back to IST after what, a couple of years?
2.5 years. Yeah.
Yes, yes. He was previously a postdoc here, and many of you remember him. He's now at the Rata Institute in the Hebrew University of Jerusalem, and he will tell us about thermal order in 3 dimensions. So, thank you.
Thanks, Pepe. Hello, everyone. It's really great to be back after 2 years, and I really love Madrid. I missed it. Okay, so today I'm going to talk about thermal order in 3D, which is basically a work that is based on a paper with some of my colleagues at the Hebrew University, at the University of Kentucky, and at the University of Minnesota. And let me start by telling you what the talk is going to be about. It's primarily going to be about quantum field theories that break global symmetries at high temperatures, which is slightly counterintuitive. So we are aware of, usually the notion that we are aware of is that systems that have global symmetries, some of which are broken, all these symmetries get restored when you increase or go to high temperature, high energies. That's the common notion that we have about any kind of systems that we encounter. There are some exceptions to this rule. One of them, which is very well known and sort of textbook material, is this thing called the Rochelle Salt. It's a sodium-potassium tartrate, which has 3 crystalline phases, and at around minus 18 degrees centigrade, there is a transition that this salt makes from the monoclinic phase to the orthorhombic phase. And this orthorhombic phase is more ordered than the monoclinic phase. So this clearly is what I mean by an example of inverse symmetry breaking. So you have a phase which has lesser symmetry, and you go to increase the temperature, and you go to a phase which has more symmetry. Okay. This is quite counterintuitive. However, for these kind of salts, if you go to something around 55 degrees centigrade, then the salt melts completely. It goes to the liquid phase, and all symmetries are restored. And this is what we are aware of. Even in case of water, you have ice, and ice has lesser symmetries than the liquid phase or the fluid phase, and when you increase the temperature beyond 0 degrees, you get back all things, all symmetries, except that there are things like the Rochelle Salt which don't, which have this phases in between which behave in the opposite fashion. And in fact, this is not the only example. There are many such examples, and which I recently learned that in the literature they are sort of known in the, people know it or have worked on these things, and they go by the topic of entropic ordering, where there are disorder to order transitions in systems, which is accompanied by an increase in entropy. The earliest of such examples goes back to the 1940s or 50s in a paper of Larsson Sager, who described a model of hard thin rods, which has an isotropic phase, which is more sort of disordered, and it transitions to a nematic phase, which is ordered. And this is accompanied by an increase in entropy. There are many such examples that appear in chemistry. For example, in the case of liquid crystals, various colloids, and even in the case of the DNA, which is an example of a complex self-assembling structure. So all these examples do exist, but one of the things that is sort of very common to most of them is that if you go to very high temperatures, all symmetries should be restored. The question that, so the first question that was asked around the 1970s by Weinberg was, can you have a QFT example of this phenomena happen? Can you describe a quantum field theory that shows this behavior? Okay, this was sort of attempted by Weinberg in 1974. He described a model in 4 dimensions, which consisted of just 2 scalar fields with their individual 5-4 terms, and a term with a quartic interaction between the two phi4 fields, such as phi1 squared, phi2 squared, you see? And he considered this model in 4D, and he showed that if you go to non-zero temperatures, for some values of the coupling, the stable vacuum with both phi's being 0 actually becomes unstable, and there is some sort of spontaneous symmetry breaking happens. And so one of the fields gets a web. Okay. So this was a very nice model. Of course, it realized the idea of symmetry breaking at high temperatures, except that this is a 5/4 model in 4 dimensions, so it has Landau poles. And so the theory is UV incomplete. So this is more of an example of what one might call symmetry non-restoration, which is that if you increase the temperature, some symmetries are broken, or rather they are not restored. But this is a model for some intermediate temperatures or energies. And then you don't know what happens at very high energies because the theory is not UV complete. So a recent take on this was, or more sort of a follow-up question to ask was whether you can have a UV complete theory where the symmetries remain broken for arbitrarily high temperatures. Okay. And
sorry, can I ask?
yes, please.
Do you need to fine-tune anything in this model for the thermal mass square to be negative, or is something?
I think it only works for certain values of the coupling between the two fields, not for all values. So that coupling needs to be negative, and that too, it has a range of values, negative values for which it works. So that's the kind of fine-tuning you need. There's some fine-tuning required even in the other models that I'm going to describe. Yeah, it's not a very generic property of these models. Okay. So we can find systems, can we find systems where symmetry breaking happens for all possible temperatures? That's the question. So the model that was considered by Komargotsky, Kai, Smolkin, Rabinovich, and a couple, Chaudhary and Choi, I think 5 or 6 authors in the paper, they actually considered a modified version of Weinberg's model. They made 2 modifications to the model. One was that instead of studying the model in 4 dimensions, they actually went and sat in 4 minus epsilon dimensions at the critical point of the model. The second modification was that they considered 2 global groups, again, but they took the ranks to be different. So the initial model of Weinberg had an ON times ON set of fields, but now they considered one field which was fundamental of the OM and the other which was a fundamental of ON minus M. With this, they actually showed that they can repeat what Weinberg had achieved, that when you increase the temperature at to some non-zero value, the symmetry again breaks. Okay. But now, because you're in a CFT, if the symmetry is broken for one temperature, it remains broken for all temperatures. Okay, there is no other scale where the symmetry might get restored, because whatever physics happens for one temperature, it's a scale invariant physics. Whatever happens for one temperature happens for all temperatures. So this was an example of a system that this phenomenon is what people termed as the persistent symmetry breaking, because symmetry breaks persistently to all temperatures. And the good part was that this model was UV complete. However, because you are working in 4 minus epsilon dimensions, this is a non-unitary model. So it has its own problems because it's in fractional dimensions. And because it's a local model, you really can't push the epsilon that's sitting here to 1 to go to 3D, because you know that there's the Coleman-Wagner theorem that actually tells you that you can't break global symmetries in 3D at finite temperature for quantum field theories. So this was sort of our motivation to study a further modification of the model in order to construct a theory that is completely unitary, which means that it sits in some integer dimension. It's UV complete, meaning that we would try to consider a CFT. And of course, this should also display persistent symmetry breaking. That's what our goal was for this work. And we use sort of the same means that we did that the other people did up till now, except now we consider some long range fields, scalar fields. And that leads to a significant changes in physics, meaning that it allows us to go and sit in exactly in 3 dimensions. Okay. I'm just going to introduce next slide. Okay. So let me introduce the model here. So this is what I mean by a long-range field. You have, instead of having a local action, these fields actually are like generalized free fields, which have a dimension which we choose in this particular case to be a very specific fine-tuned dimension of d minus epsilon over 4. The primary reason why we choose this dimension is because we want the quartic interactions to be marginally relevant. So the 5/4 would, as you can see, would have dimensions which are d minus epsilon I. Right. So these fields are not local; they are just some long range. They have some long range interactions, and we're of course in the Euclidean signature. The 1 and the 2 here are the flavors of the field. So we have 2 kinds of scalar fields, and each of these scalar fields are actually vectors. They're vector multiplets. Okay. So this phi1 is a fundamental under OM, and the phi2 is fundamental under ON minus M. These are some notations that we will be using. It's important to remember that the M that we choose is smaller than N always. And typically we'll also try to keep it less than N over 2. When M is equal to N over 2, we have what is usually called the equal rank model. And when M is N less than, not equal to 2, we have the unequal rank model. And this is the one that will be of greater interest for us. Okay. All right. So these are some quick, notations. The 2-point functions here can be easily computed because it's a Gaussian period, as I just mentioned in the last slide. The 2-point functions, 3-point functions can all be computed using big contractions. And these are some of the combinatorial factors that would be handy later on. So, okay, let's go to the actual place of action. So the interesting model is not the Gaussian model, of course, but the Gaussian model which is perturbed by a quartic interaction, just as in the case of the 5/4 model, except that we choose these, there are 3 kinds of interactions that you can have. As I mentioned in the beginning, you have the two self interactions, phi1 to the power 4, phi2 to the power 4, and then there is the interaction between the 2 fields, phi1 and phi2, okay? And throughout this work, we are always trying to keep epsilon to be less than 1. And as you can see, I mean, as I explained a little while ago, the dimensions of each of these is fine-tuned in such a fashion that you have each of the operators to be marginally relevant. They have a dimension which is d minus epsilon. Okay. All right. So these will deform the Gaussian fixed point, and you can calculate the 1-loop beta functions for the 3 couplings corresponding to the 3 fields. And the solutions to this beta function, the zeros of this beta function, can be classified into the trivial ones where G3 is 0 to begin with. If G3 is 0, it means that the 2 field theories are completely decoupled. And so you can have Wilson-Fisher, they can individually be either at the Gaussian fixed point or the Wilson-Fisher fixed points. But the interesting solutions actually lie in the case where G3 is not equal to 0. Okay, so those are the theories that remain coupled. So the zeros of the beta function, the equation for the zeros of the beta function take this particular form, and we've just slightly rescaled the couplings in this fashion for convenience. And the second thing is we've introduced a parameter alpha, because epsilon 2 could be factorized out of all these equations, and everything now depends only on alpha. Okay. There is a symmetry of these equations that when alpha goes to 1 over alpha, m and n minus m are interchanged, and g1 and g2 are interchanged. The equations remain unchanged, and so we can completely focus only on the alpha greater than 1 case and forget about alpha less than 1, because the physics would be more or less the same. Now the question is about solving these equations, and whether, of course, these are a set of nonlinear equations, so there is no easy solution to these equations. You can, of course, attack it and numerically, and you will find solutions to these equations, but we want to go as far as possible analytically. So what we do is we take the larger limit of these equations, and they turn out to simplify the equations greatly. So what we do is we take n n much greater than 1, m much greater than 1, and we keep the ratio fixed between m and n. Okay, so this is one of the nice analytical limits that you can have. And you get the zeros of the beta function produce this solution, and you can check that the only place where these the only value of alpha for which these equations allow for a solution is alpha equals 1. Right? So you put alpha equals 1, you solve these equations, and the solutions look kind of interesting. The solutions actually are degenerate. You have two branches of solutions, the plus and the minus, and they meet at these two endpoints. Okay, so you have sort of a circle of solutions, and this circle is sort of parameterized by the values of G3. Okay, so you have what one conformal manifold in this case at large n, right? And at every point on the conformal manifold, you can see that the matrix of the couplings is actually equal to 0, and this corresponds to a flat direction in the potential. Okay. Later on, we will show that there's also at large n, we can also find an exactly local marginal operator that is made out of all these double trace operators that we mentioned. Which will be two other features of the manifold is that there is one point where, namely this one, where the symmetry n minus m symmetry actually enhances to just the ON vector model. And there are two trivial solutions that lie on the manifold for corresponding to the value of G30. So if you put G30 here, you will see that the two trivial solutions correspond to the first theory being at its Wilson-Fisher fixed point, the second theory being Gaussian, and vice versa. Okay, so these are the sort of the features of the large n solutions. All right. So the natural question to ask is, of course, if everything is large n, what happens at finite n then? Can you actually see, tell me whether the conformal manifold persists to 1 over n order? Of course, this is a very interesting question because there are no known examples, I think, where a conformal manifold exists to finite orders exactly without the presence of supersymmetry. No. The x's are the ratios of m and n. So x1 is m over n, and x2 is n minus m over n. And G3, as you can see, is sitting in the solution of G1 and that of G2. So I can take various values of G3, and they will tell you what are the values of G1 and G2. So that means that this can happen only if the beta functions are No, not these. The beta functions go to 0. Okay. Yeah, these are the solutions of the zeros of the beta function. So they yeah, that's what I mean. Yes. Yes, but that doesn't lie on the manifold. That lies outside the manifold. The Wilson-Fisher times Wilson-Fisher and the Gaussian times Gaussian are outside the manifold. There are only 3 trivial fixed points, these two and this one, which we will not consider, and everything else is still in the game. Okay. All right. So the question now that we are asking next is, if you have a conformal manifold, what happens to it when you consider 1 over n corrections? Does it survive? Does it break? And the answer is, so what you can do is you can take all the couplings and you can add a small 1 over n part to it. And you can take alpha and you can add a 1 over n part to it, and then you linearize over the 1 over n terms, plug them into the beta functions, and see what you get. To leading order in 1 over n, rather to the first subleading order in 1 over n, you get these equations. But if you plug in the solution for the leading order into these equations, meaning that you plug in these solutions, you will see that this matrix is singular. So it means that not all points can survive. Not all points on the conformal manifold can survive. In fact, there's an equation that needs to be satisfied by the couplings and alpha. And if this equation is satisfied, then these are the points that actually survive the 1 over n corrections. Okay. You had a conformal manifold. We consider 1 over n corrections to the beta function, and we see that not all points on the conformal manifold survive. Only the ones that satisfy this constraint equation will be the ones that survive. Right? So now the solutions can actually be found by just considering an intersection of the constraint equation in the last slide, this one, with the conformal manifold, which was found in 2 slides before. But the interesting point is the following, that this constraint equation doesn't just depend on the G3s and the X's. It also, G3s, G2s, and the X's. It also depends on this alpha, which is a electrical parameter. The alpha was the sort of depended on the ratio of the dimensions of phi1 and phi2. So you can play around with this ratio of phi1 and phi2, and you can choose which point you want on the conformal manifold to survive. Okay, I think I can give you a diagram which makes it clearer in the next slide. What I mean to say is you can tune the alpha and you can choose which points you want on the 1 over n level to survive. And what I'm going to show you in the next slide is an example with alpha equals 1. Yeah, just a second, sorry. Right, delta alpha equals 0. This is important because you can choose any value of delta alpha, and here we choose it to be 0. And so for delta alpha equals 0, this becomes the constraint equation. And we have 2 solutions that survive 1 over n corrections. Okay, and here they are. So suppose I choose x1 to be half, meaning that I choose m equals half and n minus m equals half. Okay, did I say that correctly? Yeah, that's correct. X1 is the ratio of m and n. So this ratio is half. Okay, so if I choose m to be 2, I choose n to be 4. Okay, that's what this is. And the line corresponding to this is this blue line. This is the conformal manifold at large n. Okay, and this orange sheet that you see is the surface corresponding to the constraint equation. And the intersection between these two is going to tell you which points on this conformal manifold survive 1 over n corrections. Okay, there is one point that survives always. This is the ON point, fixed point. On the left, you have G1, G2 equals 1/8 and G3 equals +4. And that is the point where the OM times ON minus M symmetry enhances to ON. So this is just the vector model. And so this point on the vector model, this always survives. But the other point is the non-trivial point. The other point corresponds to some value of G3, which is negative. And so for different values of x1, you will have different points where this surface cuts through this conformal manifold. And if you play around with the value of delta alpha, you can actually deform this manifold so that it chooses different points on this conformal manifold. And those are the points that will actually survive 1 over n corrections. And those are the points that will have G3 to be negative. And we want G3 negative because those are the points where we will see the phenomena of persistent symmetry breaking happen. Okay. So in that sense, it's important to know which point you want. Okay. Good. Right. So there is another class of solutions apart from the one that we considered, which can be controlled analytically. So initially we had this assumption that n was large, m was large, and m over n was fixed. But we can tweak it a little bit and say that let n be large, but let's fix m to some finite value so that m over n actually goes to 0. Okay. And then we plug this ansatz that the couplings start as n, go as different orders of 1 over n. If we plug this into the beta function, we are going to get all these solutions. The thing to be noted is that at large n and finite m, the value of alpha actually gets fixed to this mod of m plus 8 over m minus 4 for any value of n. What it means is that if I include 1 over n corrections to these solutions, because these were the leading large n solutions, then it does two things. One is that it fixes the value of G3, and it reduces the value of alpha. So in order not to get complex fixed points, we can always have an alpha that is between this 1 and this alpha c, and alpha c was the one that we considered before. So what is the summary of all of these things? The summary is that the second class of analytic solutions that you can get to the zeros of this beta function for the model is when you take n to infinity, you keep m finite, and you consider a value of alpha between 1 and alpha alpha constraint, and you consider the solutions that you get for these beta functions that are G3 negative. A subset of all these, of the fixed points that you get from here is going to exhibit persistent symmetry breaking. The reason why we consider this second class of solutions, apart from having the large n solutions, is because we wanted to try and get an analytic control over solutions that have finite m and finite n, right? But that's hard to do in all generality. So this is the best that you can do analytically, that we could do analytically. Of course, you can tackle the solutions directly using numerics, and that will give you access to solutions that are finite in n and m. Okay, and numerically we check that there are a large class of stable fixed points with real couplings and G3 is negative that are necessary for persistent symmetry breaking. Okay. One interesting case is when you have alpha equals 1, which means that the dimensions of the two fields phi1 and phi2 are the same. You have M1, which means you have a Z2 group, which is the same as O1. And you have the second group to be something like O5, for example. And you will start getting real valued solutions with G3 negative when you plug in these values. And persistent symmetry breaking occurs, however, not for any value of n, but for a value of n which is larger than 17. So what I mean to say by this is that getting negative solutions for G3 is not enough to guarantee persistent symmetry breaking. It's a necessary condition, but it's not sufficient, as can be seen from this example. In this example, you get G3 negative for values above n equals 6, but persistent symmetry breaking happens only above 17. Okay, so this sort of tells you what might be a necessary condition for this to happen in these kind of models. All right, and this is sort of graphically saying the same thing, that for m equals 1, n equals 6, you have all these values of G3 that are negative, but only this orange bit that corresponds to theories that break symmetries at finite temperature. Okay, all right. So what is it that what is the reason that we consider these long range models? This slide is sort of a quick review of the idea. Usually, the Coleman-Mermin-Wagner-Hohenberg theorem actually tells you that you cannot break global symmetries, global continuous symmetries, either in a 2D QFT at 0 temperature or in a 3D QFT at finite temperature. What is the reason for that? Well, the reason is a certain set of IR divergences that appears in the zero mode of the one loop thermal integral, which appears to be something like this. Only the zero mode part of the integral in local models behaves in this way. And so it goes as log of the momentum, so if you take the IR limit, this zero mode actually diverges. This prevents symmetry breaking in these models. However, in order to bypass this theorem, and the thing that allows us to go to 3D is when you consider these long range models, because in the long range models, you can play around with the dimension of the scalar field. Instead of having d minus 2 over 2, we can have something like d minus s over 2. And when you plug it into the one loop thermal mass computation, the zero mode actually behaves in this particular fashion. And you can prevent this object from going to infinity by simply keeping the s to be less than 2. And that is precisely what we are doing. We're keeping s to be less than 2, and we're keeping it to be greater than d over 2. Okay? So this is the reason why we will be able to go to 3 dimensions and still break continuous symmetry. And that is the thing that long-range models does for us. All right. So the crux of the physics part of it is that what we want to do next, after having analyzed the fixed point structure of this model, what you can do is you can put the theory on a circle, a finite time circle, which corresponds to temperature. And you can calculate the thermal correlation functions of the scalar field here. So when you compute the thermal correlation functions of the scalar field, I mean, it's a simple computation. This is being done in position space. And you can take just x and tau to be going to 0 to give you this result where the phi's are actually just correspond to phi square. Okay. All right. So the physics is simple. The physics is sort of known. In order to diagnose any sort of spontaneous symmetry breaking in these models at finite temperature, you need an analysis of the effective potential. You need to study its, you need to minimize it. And the effect of the quartic interactions, when added to the free part of the action, as was shown in the first slide, is just to induce these quadratic terms in the action. Okay. In a local model, these would be the thermal masses, a thermal mass squared. In a long-range model, these are just some couplings of the quadratic terms because they don't have the canonical dimension for the mass. For the simple reason that the phi's don't have the canonical dimension of phi's in local theory. Nevertheless, they will still do the job if this is the effective action for the zero modes of the fields, phi1 and phi2. And if you are given such an effective action, then, oh, sorry, I forgot to say. The explicit expressions for the m phi's are given in terms of these expectation values of the phi1s and phi2. So now, okay. So this is all that we need in order to analyze the effective action. As you can see, from the first slide, let me just go back to it once. This quantity on this side is completely positive for both I equals 1 and I equals 2. So over here, you will have these quantities to be completely positive. Nothing goes negative there. So if you have all couplings at the critical point that you want to consider to be positive, so you have G1 positive, G2 positive, and G3 positive, there is no way that these masses can actually be negative. Oh, I'm calling them masses, sorry, they're the analogs of the masses. There's no way that they can be negative. And so either at zero temperature or at finite temperature, the minima of the effective potential would always lie at the values of phi's, which are 0. However, if you allow for G3 to be negative, and we did see that of all the solutions that we considered to be at the fixed point, there were solutions with G3 negative. If you plug them in, then there is a chance that one of these two masses can actually become negative. Okay, and if they become negative, then as you can see from this action, a spontaneous symmetry breaking can be induced. Okay, and one of the phi's can get a bev. So that's precisely what happens, but there are some constraints that need to be obeyed. For example, I can only consider G3 to be negative. G1 and G2 are the couplings of the 5/4 terms of the individual fields, and you can't take them to be negative because you want the model to be stable to begin with. You want this condition to be satisfied in order to avoid any runaway behavior at the level of the action itself. And in addition to this, so basically the most desirable thing is that you want to choose certain fixed points, you want to have certain fixed points where all of these conditions are satisfied and G3 is negative and small enough that this condition is satisfied. And we are lucky that in our analysis, we actually find such solutions to be fixed points of the beta function. I want to just tell you about one example, so it becomes sort of clear what we are trying to do here. Although, I mean, it's just basically minimizing the potential. If you go to the n infinity limit and you consider x1 to be fixed, and you take the dimensions of the two fields phi1 and phi2 to be the same, meaning that alpha is 1, then this effective potential is just reduces to the simple form. Okay, because the full effective potential had terms which were different, like epsilon1, epsilon2. When you take alpha to be 1, the epsilons become equal, and so this effective action simplifies considerably. Because you're considering large n, if you remember, on the conformal manifold, this condition was always satisfied, namely that the determinant of the matrix of couplings was 0, which means that this is the condition, basically. I consider the negative part of the solution, of the two solutions, and I plug it into this here. And minimize this effective potential. So I would get Z beta plus Z is equal to 0. So essentially I get Z equals minus Z beta. Z is given by this with the minus sign. Z beta is given by some terms that we computed previously, because it's the expectation value of this and this. And I get an equation which looks like this. This is equal to this object here. Okay. What can I understand from here? Well, there are two possibilities. One is that this object here is equal to 0. Okay. If this is equal to 0, then as a solution, I can have phi1 squared is equal to phi2 squared greater than or equal to 0. All right. But well, I am sort of brushing over some point here that this sort of a thing is actually possible when the couplings are actually equal. So that you don't have to consider the couplings between the phi's. And so this is one realization of what we want. You see that at finite temperature, you have beta non-zero, you have phi1 squared and phi2 squared both to be non-zero and positive. So symmetry can be broken in this way because both the phi1 and the phi2 fields are getting a wave. Okay. And the second possibility is that this is not 0. This is something finite. Okay. And that is the more general scenario because many fixed points actually, most fixed points actually satisfy this condition. And if this is not 0, then I have phi2 0 while having phi1 non-zero. Okay, so that is the condition that we are actually looking for. You're looking for phi2 to preserve the symmetry at finite temperature, but phi1 will break the symmetry at finite temperature. You get a wave as you increase the temperature. Okay. It so happens that when you consider the finite rank corrections, these fixed points don't survive. They are lifted completely. If you remember correctly, I mean, we considered the large N solution of conformal manifolds. We considered 1/n corrections on top of that, and only a finite set of fixed points survive. But these kind of fixed points are, which is the more general scenario. And so we will find fixed points where this is true, which means that we can actually find solutions where the minima of the effective potential lies around these values and not around these values. Okay. And so this is a signature that symmetry is being broken in the theory at finite temperature, which is what we call order. There is no field theory that actually can violate, I mean, there's no viable field theory that will actually violate entropy, increase in entropy, the second law of thermodynamics. This doesn't either. But this idea that entropy is a measure of disorder is not completely clear when you have these two or more of these components that can contribute to the increase or the decrease of entropy. In this particular case, as you can see, as you increase temperature, we find a solution by minimizing the action where there is order in the theory instead of disorder. You had all symmetries restored, but you're breaking some. And this is also accompanied by an increase in entropy. So this is another example of what one might call entropic ordering, if you will. And this is an interesting phenomenon. One doesn't know why this, I should not say that one does not know. I think the right statement is, if I give you a theory, you cannot tell me what properties it needs to satisfy so that this should be true. These are one-off constructions that you can make, but I still cannot outline for you the necessary and sufficient conditions for a theory so that it displays thermal ordering or entropic ordering. Okay, but this is a nice example. It's a nice example of a theory that is unitary. It's UV complete. Yeah, there's a moduli of isolated points. Is there a moduli of? Is there a conformal manifold? Not at 1/n. So isolated. But because in this theory you have this additional parameter alpha, which is the ratio of the dimensions of phi1 and phi2, you can choose on the conformal manifold which solution you want at 1/n, which is not a liberty you have for local models. You have a moduli space of vacuum, but you don't have a line of fixed points, right, at finite end. Okay. So this is essentially the physics. It's a simple model. It's with simple physics. What one can check on top of this is whether the claims that I was making, because it's an odd model, it has it's got long range fields, whether the theory is really unitary or not. Okay. Because the previous models all were local models. However, the authors considered the models in fractional dimensions, and it was shown by these authors here, Holger Wurst, Richko, Boltko, and Rees in around 2015, that you can have some interesting operators in fractional dimensions called Evanescent Operators, which vanish in integer dimensions, but nevertheless, in fractional dimensions, they exist. And for a simple theory like a 5/4 theory or like a Wilson-Fisher fixed point, this sort of theory, these sort of operators can actually have complex dimensions, meaning that the theories in fractional dimensions come with this additional oddity that they are non-unitary. Okay.
But those are local.
Local operators. Yes, local operators.
Local theory.
Local theories, yes. Local theories. Yeah, but the construction is can be done even for these fields in these models. So that's right. But if you consider the theory in 3D, then we don't have those kind of operators. Okay, and that is what we have. So unitarity in this sense is what we really have, because we are in integer dimensions. Okay. However, it is true that the long-range QFTs have a spectrum that is different from their local counterparts. So there might be some surprising sources of non-unitarities, but we are not aware of any per se, or haven't found any in the literature either. So for all we know, they're unitary and well, and what we can do to the best of our ability is to check whether the model is unitary or not at the level of the low-lying spectrum. That we can do by computing the anomalous dimensions of certain primary operators in the theory. Okay, so namely the quartic and the quadratic primaries in the theory, and that is what we do. We take some quartic operators in the theory, and we want to compute their anomalous dimensions. Okay, so we start with the operators that are there at the Gaussian fixed point, and we deform the theory with a quartic interaction. And so to leading order, of course, this is the Gaussian result, but the correction depends on a 3-point function. This is simple conformal perturbation theory. The coupling here corresponds to the critical coupling. And you can do an OPE here to reduce it to a 2-point function, and then perform an integral, perform this integral over a thin shell, okay, to obtain what is an analog of the Callan-Symmetry equation for these operators. Okay. But these are not the operators that are present at the IR fixed point. These are the operators of the UV fixed point. And we are looking for the anomalous dimensions of the operators of the IR fixed point. So we define the primary operators at the IR fixed point to be some linear combinations of these operators at the UV fixed point to leading order in epsilon. And these operators actually have a 2-point function which looks something like this. Okay. And their Callan-Symmetry equation can be derived from using the Callan-Symmetry equation of the operators in the Gaussian theory. Okay. And essentially, what we can find is that the anomalous dimension matrix for these operators has a simple form in terms of known quantities. So you know what these objects are. These are the OP coefficients. You know what these are. These are the coupling constants. And the second equation actually follows from the beta functions themselves. So the beta functions have this sort of a structure. So anyway, the important thing is that that we know what the anomalous dimension matrix looks like. And moreover, you can simplify this equation by taking these vectors here to be the eigenvectors of the anomalous dimension matrix. And that will simplify things tremendously. And you will see that the Callan-Symmetry equation looks something like this. Why is this important? Because this simply tells you that the anomalous dimensions that you want to check whether they are real or not are just eigenvalues of this matrix that you have here. And this matrix, we know what the form of it is. Okay. You can simply take this object and you can diagonalize it, and you will find a solution which has the anomalous dimensions of the individual operators on the left, the anomalous dimension of this matrix here, and epsilon. Okay. And the scaling dimensions of the primary operators are actually related to this quantity here, this one. So the scaling dimensions of the primary operators, of the 3 primary operators at the IR fixed point, can be written in terms of this omega, which I can substitute from here. So you can see that they are all d minus epsilon plus an anomalous dimension. And I can compute all these anomalous dimensions, as I said, because I know its expression. And I find these three results. I find one anomalous dimension, which is completely real. If I plug it into this equation, I will get one operator, which is slightly relevant. So if delta is equal to d, that is marginal. A little more than d is relevant, a little less than d is irrelevant. So one of these operators is completely irrelevant, and two other operators have dimensions which are given by this. Okay. The important thing to check now is whether this is real. If this turns out to be negative, so not real. This if the thing inside is positive. If this turns out to be negative, then it means that gamma plus minus has a complex object, and that the theory is non-unitary. Well, luckily, we actually see that it is in fact positive, and gamma plus minus is a completely real object, which tells us that these dimensions are completely real. At finite m and n, you actually have delta plus prime and delta minus prime, where the plus prime is weakly irrelevant, minus prime is weakly relevant. And you can take the n infinity limit of these objects, and you will find that the delta plus prime actually becomes exactly marginal. And this, at n infinity, this exactly marginal operator is what I had promised in the very beginning, was the one that corresponds to the conformal manifold. So there is a construction that is available of an operator which is local and which is exactly marginal, and which will correspond to the conformal manifold. But as you see, I mean, if you go to finite n, this becomes weakly irrelevant, which means that it ceases to remain marginal, exactly marginal. And this is another way of saying that the conformal manifold gets lifted at finite n. It's not there anymore because you don't have an exactly marginal operator corresponding to it. Okay. So the first check that these models are unitary works at the level of quartic operators. You can consider quadratic operators, and we checked their dimensions for both. This is the answer for a equal rank. For alpha equals 1, but you can have alpha not equal to 1, and they will still remain real, which can be checked numerically. So the real anomalous dimensions for both these quadratic and quartic primary operators in the theory provide evidence that these theories are unitary. Okay, it's not a proof because we haven't checked all possible correlators and all possible anomalous dimensions. But as far as we know, this model is unitary. Then there is the second question, which is of conformal invariance. And there's an issue with these long-range models, which I avoided from the very beginning because we did not need it. And that is, these theories don't have a local stress tensor. Okay, they're completely the local stress. You cannot have a construction for the local stress tensor. So in the absence of a local stress tensor, it is usually hard to establish the existence of conformal invariance, especially at the level of the algebra. For the long-range Ising model, evidence for or a proof of the conformal invariance of the model was actually given by Richkov and Paulos and company around 2015. And because this model is so similar to the model that they considered, they had a single phi field and with a phi-4th interaction. And the kinetic term was the same that we have here. Because of this extreme similarity, it seems quite evident that even in this model is probably going to be conformally invariant. What we can do is we can provide a quick check at the level of correlation functions. So usually in scale invariant theories, which are not conformally invariant, if you take two different operators of different dimensions, it's not zero. It has a structure of this form. So you take a quadratic operator, you take a quartic operator, and you have a form which is this. C0 is put to 0 by the presence of conformal invariance. Okay. And what we can do is we can actually, we actually checked in our case, we took the analog of our quadratic operator and our quartic operator, and we computed this sort of a diagram. And we showed that to the order that we are concerned with, which is the leading order in epsilon, this 2-point function is in fact 0. Okay, this gives an evidence that there is a conformal symmetry at the evidence at the level of correlation functions that the model has conformal symmetry. We made some additional checks of 3-point functions. That's another thing that conformal symmetry tells you, fixes for you. The 3-point functions have a very definite structure in conformal field theories. And we checked that whether that sort of a structure arises for these operators that we found at the higher fixed point, and indeed it does. Okay, so we have very strong evidence that conformal invariance is also something that is present in this model, and they're not just scale invariant fixed points. All right, so that's about it. What we discussed is that we improved upon some previous attempts to build a unitary and importantly unitary, but also UV complete vector model in 3D that exhibits persistent symmetry breaking. To the best of our knowledge, this is the only model in 3D that displays this behavior, while also including 1/n corrections. We have a better understanding of the necessary conditions that we need in these models to get persistent symmetry breaking, but about sufficiency conditions for PSV, we still don't know what are the kind of models, what are the kind of sufficient conditions these models must have so that they have symmetry breaking always at high temperatures. So how do we go about constructing them? Some of the future directions, interesting future directions could be the following. You can try for a systematic classification of systems that undergo persistent symmetry breaking or entropic ordering, whichever language you might want to use. And maybe conformal bootstrap at finite temperature can help us in this endeavor. Because now we are in the realm of conformal field theories. The long-range models that we considered here can be described, are found to be the theories that are at the boundaries of bulk CFTs for very specific values of the long-range parameter. There are interesting bulk phases that we discovered in this theory. One might wonder what kind of interesting bulk phases. We discussed some interesting phases for this model. One might wonder what interesting bulk phases it can correspond to if these theories are actually at the boundary of some bulk CFT. And finally, people are recently discussing QFTs on ADS and S matrices in these theories. Long-range conformal field theories actually are the theories that lie at the boundary of a manifold, an ADS with a fixed background, because those theories don't have a stress tensor. The corresponding boundary theories don't have a stress tensor, and so the good question to ask whether the S matrices of QFTs on these fixed ADS backgrounds, whether long-range models have something to say about these as well, and whether persistent symmetry breaking can have some manifestation in holography. So that's all I have to say. Thank you.
Thank you, Ritam. Are there questions for Ritam? Yes.
So do you expect the fixed point is the fixed point?
The fixed points, yes. The fixed points. So you mean we actually have these are some of the fixed points that that we checked at large n, and we showed you that there are equations that that many of the fixed points are lifted at 1/n order.
does any fixed point survive the next one?
Yeah, these fixed points not just survive at 1 over n, but we will show that they also will survive at 1 over n, 1 over n squared n. And in fact, numerically, we know that there are a lot of fixed points that survive at finite m and finite n. So, you know, we have evidence that that is true.
The deformations between the parameters that you were assuming that the coupling constants were small and you were making a perturbed series in them. That's right. But then the solution to the beta function, the conformal manifold, was taking this happens to be order 1. So
No, that was because of the scaling that I performed. Actually, I don't know where it is, but it's really somewhere in the beginning. I just scaled out the epsilon because they were present everywhere. Yeah, it's still.
More questions? Anybody on Zoom? Okay, you mentioned the ADS version of this. I was going to ask you about that. But I noticed that you consider interactions as local in the standard sense.
Yeah.
So your generalized free fields, you write a Lagrangian for them at the quadratic level is no local. But you choose the to be local, which after all is a little bit arbitrary, because if you start with a non-local theory, why you should consider local interaction? And if you consider the ADS version and you prescribe Witten diagrams, those will induce non-local interactions in the boundary theory, no? Because they are local in the bulk, but they don't have to have this form of product of instant point in the bulk.
Okay. It's possible, yeah.
So
no, I don't say I'm not claiming that this specific model has some model has some bulk.
I know,
but yeah.
My question is, if there is another set of models,
Yeah.
which are the type of generalized free fields that you would get from the bulk, in natural theories in the bulk, which would be local in the bulk, which would be yet different from these and maybe have similar.
Whether they can have symmetry breaking of this kind?
Yeah.
Actually, in the case of QFTs and ADS, there's a paper by Dean Carney and I don't remember the other author who actually showed that they can bypass the Coleman theorem. But the point is, in the example as well, I think the symmetry is broken at for some finite value of the energy parameter, but then gets restored again. Okay, so they have what I mentioned in the beginning, an example like Rochelle Salt. And I guess the thing that's special about these theories is that the only scale that they have per se is the temperature. And so once the symmetry is broken, it's broken. But in ADS, I guess there is the ADS scale, and you're not considering a QFT. Right now I'm just talking about the QFT in the bulk. There, I don't think you can have persistent breaking. So whether a corresponding theory in the bulk can have a boundary can have persistent breaking also, I'm not sure. Especially because I mean, if you have non-local couplings, then first of all, it will be hard to control the perturbation theory by itself. So I don't know how to go about it.
Yeah. Well, if the theory is, if the generalized free fields are sectors of ordinary large N theories, you don't expect to see a persistent breaking, because that will be just a sector of a theory which has an infinite number of generalized free fields in the Larsen limit. And the theory, the underlying theory will have a Lagrangian, local Lagrangian. So probably it will behave normally. No? Like say, try to embed this into some
Yes, but
standard Larsen gauge theory.
are you talking about a completely decoupled sector? Something that doesn't interact with the rest of the.
No, I'm saying that maybe you cannot achieve that.
It seems so. I guess so we have, I think we have such generalized free fields that appear, but whether you can construct a consistent sector where it shows symmetry breaking in that sector and forgets about the rest, I'm not sure. It needs to be completely decoupled, or maybe if you can show that the effect of the coupling with the rest of the fields doesn't affect the solutions that you get from the finite density, perhaps it can work.
Okay, are there more comments, questions? Nobody online, so then we thank Ritam again. Thank you.